Hi guys, this is Schloegel. I am Blazytko, and today we talk about the next generation of virtualization-based obfuscation. Just a few about us slides. So I'm Tim, I'm the chief scientist, co-founder of Mproof, an embedded security firm where I design software protection systems for embedded devices. And I also give trainings on code deobfuscation and reverse engineering techniques. This is Moritz. He is an old coworker of mine. He is a last year PhD student at CISPA in Saarbrücken. He works on bug triaging, fuzzing, and also reverse engineering in general. And he was, together we built a code obfuscation scheme we are talking to today in the later parts. And so, now we start officially. Today we talk about 3 different topics. The first thing is VM-based or virtualization-based obfuscation, what it is, how it works. Then we take a closer look on the recent attacks on virtual machines, how they work, why they succeed. And then we shift over to a new topic, to some new obfuscation schemes we start seeing in real-world applications right now in the high-end market of code obfuscation. And there we will talk about the concepts, the design decisions, and why current attacks don't work anymore. So let us start with an easy motivation. First, why do we want to talk about code obfuscation or virtualization-based obfuscation? Because it is one of the most common and strongest techniques to complicate reverse engineering attempts. You will find it mostly in areas where you want to protect your intellectual property, mostly DRM systems. So if you watch Netflix in your browser, if you have your mobile banking applications, if you play games, you use programs which basically have virtualization-based obfuscation deployed, but also some malware guys start using VMs. So let us talk first about virtualization-based obfuscation in general. So the typical analysis scenario is that we have a piece of code, and this piece of code might be an algorithm which is protection worthy. Right now, we would open the binary in IDA or binary ninja or whatsoever, and basically could just analyze what's going on. So our goal is to protect that or to prevent that. What we do there instead in virtualization-based obfuscation is we translate this piece of code into a made-up instruction set language, like another assembly code for a software virtual machine. So, and now you think about how is code represented in binaries as data, which has some meaning for the software, for the hardware VM, like x86. On software, it's comparable. This made-up instruction set is just encoded as a sequence of bytes, which doesn't make any use for us reverse engineers. So, and then what we basically do is replace the original code with a pointer to a bytecode, where this bytecode represents the original code. And then we call a function, the VM entry, which is basically a virtualization interpreter in software that takes the bytecode as input and performs some computations based on the bytecode. You can think about it as this is a JVM and this is a JVM code which is interpreted by the JVM, just in an obfuscation scenario. So, and if we would open this data blob, it wouldn't have any meaning for us right now. So typically on the binary level, we have some concepts how VM is represented. The most important thing is first that we have a VM entry and a VM exit. You can think about the VM as some dedicated function which has its own prologue to save the outer VM, the outer CPU context, the native execution context, and then prepares everything like internal registers, keys, and stuff like that, which is needed for execution. And in the end, when we leave the VM, we call the VM exit or the function prolog, which basically restores the outer state while preparing some output register or something like that. So the VM entry and the VM exit are these code components which basically do the transition between the native code and the VM code and the other way around. Then we have a VM dispatcher. The dispatcher is the software implementation of the CPU's fetch, decode, execute loop. It starts by fetching some bytes of the bytecode and decoding the actual instruction. Then we forward the virtual instruction pointer and pass the opcode, the operation which basically represents if we have a virtual addition, a virtual multiplication, or what so on. And then we call this dedicated function called handler, and then the handler performs the actual semantics on the CPU state. And after we finished, we basically go back to the beginning and restart the fetch, decode, execute loop by fetching the next instruction and so on. And there is a concept of handlers and handler table. A handler is more or less a piece of code which implements a specific CPU instruction, like a virtual addition or a virtual push. And a handler table is just a jump table or a table of function pointers which contain all addresses of the individual VM instructions. And if we have a control flow graph like that, we can do a good one-on-one matching about what's going on. So, for instance, on top of here, we have the VM entry, where we prepare everything. Then we have a large fetch, decode, execute loop, where we, on top of here, look up the current instruction, which we need to execute based on the bytecode, transfer the control flow to one of the individual handlers, then perform some semantics and jump back. Only one handler doesn't return to the fetch, decode, execute loop, the VM exit, which is called to leave the VM. And if in case you wonder, this is an old example of VM protect. So, two more examples how this may look like in code. We have RSI, which is a virtual instruction pointer, which points to the current location in the bytecode. Here we see that we fetch a byte from RSI, that we use it, that we put it into arrayx, and then use arrayx as index into a table, which is known as a handler table, to basically look up which handler, the ends handler encoded in arrayx, we execute. We also have an example handler here, where we have two arguments, one at RBP, the other at RBP plus 4. Once we loaded it into registers, we perform some arithmetic operations, then store the result of the operations back into the VM register, perform some flag operations, and jump back to the dispatcher. These are some examples how current VMs may look like. So, given that, how would one break these VM-based obfuscation schemes? How to reconstruct the original code? So remember, right now, the original code is represented as a piece of bytecode, which doesn't make any meaning for us. So what we would do is, first, we would have to understand the VM architecture and the context, like where is the bytecode, where is the instruction pointer, where are handlers, what the handlers do. In the second step, we have to reverse engineer the handler semantics, like this is an addition, this is a multiplication, and stuff like that, and figure out the instruction encoding. Once we figured out the instruction encoding, we can write a custom disassembler for the bytecode, such that we basically give the sequence of bytes some meaning. And based on this assembly, we can then start reconstructing the control flow and finally reconstruct the high-level code. So, for instance, think about we have reverse engineered this instruction format where we have 1 byte opcode, 1 byte register, and a 2nd byte register. And we have this sequence of bytes. we would walk byte by byte. We take the first one and know this is the opcode, this is an addition. Then we walk to the next byte. This is a register. Since this is the 1, we put R1 here. And then the second one is a 2, so we put R2 here. And then we know the instruction is only 3 bytes. So the fourth byte will be the next instruction, which then decodes to multiplication of R1 and R5. So, and now, based on this, we could reconstruct the high-level flow. For instance, we can say this computes R1 plus R2 times R5. This is the 101 for VMs. So, in practice, especially if we look at solutions like Temida or VM Protect, which is common in Spotify, in gaming, and in some other things, they deploy some hardening techniques which make current VMs a bit more complicated. And overall, they deploy more or less 5 different techniques. One technique is obfuscating individual VM components. So, as we already have seen, a simple instruction is just an addition or a multiplication or an XOR. So they are semantically really simple, and normally you can implement it in 5 to 10 instructions. However, you want to complicate it. And therefore, you can apply additional common code obfuscation techniques, such as code substitution, opaque predicates, insertion of junk code, and stuff like that, to make the individual handlers look more complex. So, in other words, increase the instruction per handlers to make it more difficult to analyze. Second, you usually have a limited set of different handlers, like, for instance, 50 different handlers or something like that, to where one presents an addition, one a multiplication, and so on. Analyzing 50 handlers can be done pretty easily manually. But what you usually want is to force them to make it as hard as possible and to create additional workload for the reverse engineer. And what you do therefore is that you duplicate existing handlers and deploy way more than 60 handlers by creating handler copies. So, for instance, you use now 10K different handlers, where you increase the workload of the reverse engineer and basically enforce him or her to use automation. So, meaning, instead of having some handlers, we just add some duplicates where all the different handlers also look a bit different because we insert other junk code or we apply different obfuscation schemes local. So in the end, we just make them syntactically different in representation and deploy some copies. So up until now, we have more complex handlers and we have more handlers. But we have 2 central places in the VM. One of them is the central dispatcher, where each handler jumps back to when it's finished. And what we could do as attackers is that we could set breakpoints at the VM interpreter, at the dispatcher, and basically dump all the things. So it would be pretty easy for us to dynamically observe what the VM is doing. And therefore, the idea is to get rid of the central VM dispatcher by inlining the dispatcher at the end of each handler. So instead of having something like that, where we have the fetch, decode, execute loop of the dispatcher is connected with all different handlers, and these all jump back to the same dispatcher, what we instead do is that we inline the dispatcher at the end of each handler, so creating some overhead in size, but while making it also more performant on the execution level, because you have a jump, you reduce a jump. So basically, with that, you don't have this central data structure anymore, which can be easily instrumented. And by the way, this is a technique which has been used in obfuscation in the last 15 years or something like that. But the technique is way older. It goes back to the early 80s, where research has been done on making software VM implementations more efficient, like this JVM. And the other technique, now where we omitted the global handler where we omitted the global dispatcher, we still have a global handler table, this data array of function pointers. So what we do to get rid of that is that we basically modify the VM instruction encoding. So instead of doing opcode operation operand 1, operand 2, we extend it by putting or encoding the next handler address at the end of the instruction, for example. And therefore, the dispatcher, the inline dispatcher, would just read the next handler address from the bytecode and jump to that. Okay. And also, this is also an optimization technique that goes back to academia in the early 80s. So, and the last hardening technique is called bytecode blinding or bytecode encryption or bytecode encoding. The idea is to basically encode the bytecode in some form such that your disassemblers won't work statically. So right now, you could reverse engineer the VM, put in the bytecode there, and manually decode it. However, if you write your disassembler based on the VM, because you know instruction encoding and stuff like that, you still can't easily apply your disassembler because now you have some bytecode encryption. This meaning the bytecode is decoded at runtime in a control flow sensitive way. So in other words, the first handler basically has a hard-coded key, which is used for decryption of the next byte. And then the key is updated based on the current VM context, basically enforcing or preparing the key for the second handler. And then the second handler uses the modified key and only is in the right state if the first handler has been executed before. And therefore, the current handler always decodes the next handler and updates the key. And with that, you have a control flow sensitive instruction decoding. So, given a current handler where we fetch the operands from the bytecode first, then we perform some semantics-based operations like an addition based on the VM state. Then we fetch the next handler from the bytecode, and in the inline dispatcher we jump to the next handler. What we do now is that we add some decoding. So, like based on the fetched bytes we read, we do some decryption based on the current key. This decryption is not an AES, it's more an XOR with a constant or something like that. And then we decode the operand here, and this decoded operand is then used to update the key again, and then we use the key to decode the next handler and update the key again. So, therefore, we have some context in the VM execution. So, question, how do we break such hardened VMs? Well, the techniques are quite similar. Our goal is first to understand the VM, to locate the VM entry, so where's the beginning of the VM, where's the bytecode located, and then if we know where the handlers are, we can use traditional program analysis techniques, like we will have a look in some minutes, to automatically simplify most of the handlers. And then what we can do is that we can write a control flow sensitive disassembler, which, for instance, using some DBI or some symbolic execution or whatever, basically starts at the VM entry and automatically follows based on the bytecode the VM execution, and therefore corrects the decodes the correct keys internally automatically, and then can apply the disassembly on its own. So, question is, what kind of attacks exist to simplify existing VM handlers? So, one of the easiest and one well-known one are instruction removal or compiler optimizations, or a specific set of compiler optimizations. Think about this code. So we have, I don't know, around 10 to 15 lines of code here. what does this exactly do? Or is there anything which is not required? So, yes. Let's have a look at these examples. Here, we move a constant into EAX. And then we overwrite EAX with another constant, making the first instructions useless. So this is dead code. Same as we move a register into itself. Doesn't also make sense. And also we add 0 to something, which doesn't also make much sense. In other words, in these cases, we could just omit these instructions and the state wouldn't be affected anyway. This technique is known as dead code elimination. We can do better. So we have this one, where we move a constant into a register and then add another constant to this register. What we could do is, we could at compile time compute the constant and just move it in there, reducing one instruction. This is known as constant folding. Then we have instructions like that, where we move a constant into a register and this register into another register. So this is also nonsense in this case. We can just put the constant here and directly write it into the destination register. This is known as constant propagation. And finally, what we could do is instructions like push EAX and pop EAX, where EAX is not required anymore, or where we have a not and not a not, which is also not required anymore. So we could just remove those again. So, and then we end up with these instructions. This technique is known as people optimization. And in the end, we simplified everything quite a bit by using just compiler optimizations. So if this is a VM handler, which looks like that, where we have some really large basic blocks, which just contain a lot of junk code, with compiler optimizations, it's shrunken to the minimum, and then knowing the structure of the VM handlers as discussed before, we can now easily spot what is where. Like on top of here, we have the decoding and some key updates. Then we have the actual semantics, like the addition or the multiplication. And in the end, we have the inline dispatcher. And this just by using compiler optimizations. And there's some research and also some companies which have in-house techniques where they basically start with binaries, and then you take the binary, lift it into immediate representation, like the LLVM intermediate representation, and then you can apply lots of different compiler optimizations to the code, and then you can take this optimized intermediate language and spit it back by compiling it to the architecture again. And this way, you can build automated deobfuscators. Another technique is known as symbolic execution. A symbolic execution is some kind of computer algebra system for assembly code. So, if we have a piece of code here, what we would do in a symbolic way is we execute instruction by instruction and propagating their symbolic values. Like we have the memory cell RBP, which is then stored into RCX. And RBP plus 4 is stored into RBX. Then we perform a NOT of RCX, where we know that RCX is just RBP. So this NOT RCX becomes NOT RBP. And the same goes for the second operand. Now we perform an addition. And we already know that the first parameter is currently not RBP and not RBP plus 4. And now the computer algebra system has some kind of hard-coded term rewriting rules, term simplification rules. It might recognize that this pattern is the same as the logical NOR. And so it could rewrite it in a simpler formula, like the NOR, which then is propagated into the memory cell at RBP plus 4. Then, finally, we perform some flag operations and jump back to the dispatcher. But if we symbolically execute the whole handler, we can easily derive its core semantics, like that we take two arguments, perform this NOR operation, and put it back here. And with that, we basically get a symbolic summary about the handler, which allows us to easily pinpoint what's going on. And then we have also something which is called program synthesis. The idea of program synthesis is that you use some mathematical formula or some code as a black box. So you don't analyze the code itself. Instead, you use it as an oracle, where you put in random values and observe its output. For instance, like emulation. And you put in some values, observe the output, and store it somewhere into a database. And you do it some time. And then you have a set of input-output samples. And then in synthesis, the goal is to do some stochastic learning algorithm, which automatically tries to find mathematical formulas which have the same input-output behavior. And in this case, we might learn something that this is the same as x plus y plus z. So, and we can, for VM-based deobfuscation, we can even perform lighter attacks. So-called codebook attacks. What we know is that VMs have a predictable instruction set, like an addition, a multiplication, an XOR, and stuff like that. What we could do is that we generate a table of different predicted instructions or handler semantics, and then pre-compute a lookup table. Like for this input, it's the semantic, just a bit larger in theory. So, and then you can IO sample a handler and look up what it looks like. And you could then even, if the handler should be obfuscated in any way, you can also additionally use a SMT solver to prove that the symbolic derived code and your template are semantic equivalent. So in case you are unsure if this is correct, you can mathematically prove that. So given these kind of attacks, we can summarize that existing VM handlers have some shortcomings. So the shortcomings are that they have predictable instruction semantics with meaningful mnemonics, meaning they are short, they are clear that they can be entitled as this handler performs an addition, this is a multiplication, and so on. And because they are so simple, they are also vulnerable to synthesis-based attacks. And the other shortcoming is that individual VM components are independent of each other, meaning the obfuscation which is applied can be deobfuscated on the handler level. They only are applied locally. So therefore, if something is dead code, it's enough to recognize it on the handler level. So I, for instance, can isolate each handler on its own and simplify it because they don't depend on each other. And therefore, the obfuscation is limited to local constants. So, giving this VM attack landscape, where we have compiler optimization, symbolic execution, and program synthesis as the major building blocks, and different application scenarios like static and dynamic and so on, we can conclude that current VMs are vulnerable to all these attacks. However, there's something going on in industry and also in academia. There's a new generation of VM-based obfuscation up on the horizon and also already deployed in some high-end real-world applications, which take VMs to a next level. They basically rely on old concepts, but reinvented them and modified them slightly by adding two new design aspects. And the design goal was to basically be resilient against all these attacks we discussed before. So the question is, on the high level, what do they do? So the first design principle is basically that we build complex and target-specific instruction sets. So we don't want any easy handler semantics anymore, like an addition, a multiplication, or so on. We want to have them more complex, longer, and also target specific, meaning that based on the binary we want to protect, to obfuscate, that we build VMs which are targeted to this binary, like building handlers based on code sequences that sum up in the original code. So, and therefore, what we do is that we generate handler semantics based on instruction sequences from the target program. This results in complex handler semantics, which first introduce a lot of diversity, such that they are not predictable anymore, but also they provide resilience against synthesis-based attacks, or more powerful synthesis-based attacks, because they become so hard and so complex that you can't easily learn them anymore with some stochastic learning approaches. And they can also build in a way such that they are control flow dependent or data flow dependent. Meaning, if you have a chain of code where computations rely on each other, we could take parts of that and put it into a dedicated handler. This is the first design principle, making handlers more complex. The second one is that we combine or intervene VM components. Meaning, instead of leaving everything local to the handler, we start interlocking handlers, semantics, such that we enforce an analyst to perform a cross-handler analysis. So this could be realized, for instance, by arithmetic encodings, where one handler performs some partial encoding, which is then further encoded in the next handler, and then further encoded, and 10 handlers later, it just collapses to the original semantics or something like that. So basically adding some control flow dependent encoding across different handlers. Same goes for data flow dependent or multi-threaded opaque predicates. If you know that one thread interacts or starts before another thread, this one thread could change some global data into the other thread and stuff like that. While this looks like this might be a valid branch, instead you just switch it, and you, from an attacker perspective, knows that this will never be the case at this point. So basically forcing the analyst to take a look at the control flow on a larger scale, or to also expand towards multi-threaded analysis and stuff like that. Or you can also merge handler semantics by doing some arithmetic encodings, such that based on certain inputs, you trigger a different behavior of a mathematical formula. So, however, no matter how it is realized in the real world, the consequences are the same. The analysis effort rises enormously. And with that said, with these design principles introduced, I will now hand over to Mo, and he will talk about Loki and what we did there.
Right. Thanks a lot, Tim. So I'm excited to talk about Loki, and I'll give you the disclaimer first. This is an academic prototype of how we implemented such a next generation VM. However, I want to emphasize the whole industry shifts towards these designs, these techniques we're going to look into in a second, but good luck getting a company to reveal what exactly they are doing. As with all academic things, there's a paper. So if you're into reading paper, there's the link, and there is the look of the paper. Let me quickly thank all our contributors who made it possible to write that paper and present our work here today. Now, think back to the VM handlers, the simple VM handlers Tim presented to you. That's the exact same instruction encoding Tim showed you before. And for the sake of the following techniques, we will use a mathematical notation to represent our handlers. And the second thing we will need in a second is constants. So we'll just update our instruction encoding and we'll just embed the constant there. And we will use the letter C to denote constants. And this is how this could look like when we use a constant. And the third and last thing we need before diving into the juicy details is the term instruction semantics, which I will use to talk about what a handler actually computes. So the instruction semantics of the handler f, the function f, would be x plus y. All right, so now we can go to the starting point of Loki. Can we do better than these simple current VM handlers? And the answer is naturally yes. So we'll dive into a couple of techniques, and we'll start with merging instruction semantics. So we take the instruction semantics of two different handlers and we put them into a new single handler. Now, such that we can address the original instruction semantics, we do need our key k, which allows us to select either x plus y or x minus y left shift c in this case. We say these are key-dependent instruction semantics, and if we think about them in a control flow way, it would look like something like this. So there's an if, there's a branch, and there's either we are going the x plus y way or we are going the x minus y left shift c way, right? So that's easy to isolate, easy to attack. And really what we ideally would love to have is one gigantic basic block with all the instructions in there. And fortunately for us, there's a simple technique, a simple trick to achieve this. We can use the so-called polynomial encoding. So basically, these two are the same. The one is using the if, and the other is using a clever combination of addition and multiplication to do the same, but be in a gigantic basic block instead of having these branches. The neat thing here is that this causes a tight interlocking of instruction semantics, which is not that easy to attack. And even with something simple like a polynomial encoding, we can already prevent instructions from being removed trivially. So the complexity helps a little bit with symbolic execution, but there's a couple of aspects we can improve upon. And the first thing we are looking at are the key checks. So these are simple comparisons, and there's no reason to use something as simple as that. What we could use instead are mathematically hard problems. So the first one, the key check on top, is factorization. The question is basically, is our key k a factor of some large integer n? This could be familiar to you from the RSA background. And it's a mathematically hard problem. We'll see in a second why that's cool. Let me just say the other one is quadratic residues, and it's a similar hard question. Now, the nice thing about these problems is there's a huge search space and there's only a small solution, and there's no partial solution. You can't like limit or make the search space smaller. You have to find the right solution by brute force or whatever. And this is very neat because this leads to SMT hard encodings for instruction selection. So the huge search space that cannot be pruned to something smaller, there's no partial solution. That's exactly what SMT solvers are doing internally. And this way you can no longer use the SMT solver. This is very nice because Tim presented you before the code books, which use the SMT solver to compare whether our handler, the handler analyzed, is something simple like x plus y, right? But there is other stuff we can do with our key checks. So instead of having the quadratic residues here, we could use a partial point function. And we'll see in a second what a partial point function is. I'll show you first an example of a partial point function, and there are many forms of this. So this is just one example. This one is synthesized, so it's basically made up according to some rules, and there are two major rules. The first one is this point function must return 1 for the correct key. So the key for the bottom instruction semantics is 0x1336, and that is so we can select the instruction semantics, right? And the second rule, the second constraint we impose is that for the key of the other instruction semantics, so the one on top, it must return 0. This way, it will cancel out and it will not impact the computation. Now, that's exactly 2 points for which there is a requirement, there's a definition what should happen, and that's why it's a partial point function, because obviously there's many more inputs you can throw in. And if we throw in other inputs, we just have not defined what should happen, and there's just random garbage being spit out. And that's cool, because what we've seen is program synthesis throws in random inputs and records the outputs. That's the I/O sampling you use before learning the function. And if you just learn random garbage for most of your inputs, you can no longer synthesize an expression. Now there's a huge caveat. This only works for a static scenario where you assume the attacker has no access to the keys at runtime. And we can do better than that. So to specifically target all program synthesis attacks, there's one technique we can use. And the intuition is basically, instead of having these simple generic handlers here on the left side, like an addition or multiplication, which are called one after another, we could have one complex, large handler, which does all of that based on what the program needs. So on our handler, instead of having this simple instruction semantics x plus y, we might find something like x plus y plus x plus x. The thing really here is what we need to look for is that this is target specific. So the target program which we are obfuscating is running this operation. Now what this leads to are semantically complex arithmetic operations. And this complexity helps us because synthesis is excellent at coming up with very short expressions. However, the more complex the expression becomes, the success rate drops rapidly from synthesis. And if your expression is complex enough, synthesis can't cope with that. And how can we find such semantically complex operations in our program? That's what I brought you a small example for. So there's 4 assembly instructions on the left-hand side, and on the right side there are the same instructions in static single assignment SSA form. And basically what we are doing is we recursively replace uses by their definitions. Now, for EDX3, which is defined as EDX2 multiplied with 0x10, basically we can look up the use of EDX2 and replace it by its definition. And I know that's a very simple example, but you could keep going like that and make that more complex. In our handler representation, mathematical notation, this would look like this. The nice thing here is about such semantically complex operations, they help us against synthesis. Their inherent higher complexity also helps us in terms of preventing symbolic execution, which has to deal with this complexity. However, there's also a specific technique with which we can target symbolic execution. So let's look at that. And the idea is similar. Instead of having our instruction semantics as simple as they are currently, we replace them with another expression that does exactly the same. So it computes the same, however, is more complex. And this could look like this. So it looks more complex, it looks scary, but it computes the same. And we could do this with the other instruction semantics as well. And this leads to syntactically complex expressions. So the underlying semantics, the underlying computation is the same. However, it looks scary, it's larger, it's more complex. The way how we get there are so-called mixed Boolean arithmetic expressions, which for short are called MBAs. And basically, on the left side, we have our expression, which we want to make more complex. And we have a couple of rewriting rules. The rewriting rules are basically a lookup of a simple expression to a more complex one, which does the same. And what we're doing is we simply pick the expression or some sub-expression like x plus y. We look that up, we replace that, and because the rewriting rules are the same, the expressions are the same, and that's how we were traditionally doing MBAs. Now there's 2 things that are not so good that I would like to highlight. And the first is this 47. There's just only 47 rewriting rules. Well, that's because we've used to come up with them handcrafted. So you either by chance found out this is the same expression as another one, or you looked into books like Hacker's Delight, and that's how we came up with these rules. But instead, we could do better. So what we did is we used enumerative program synthesis. Basically, we've generated all possible expressions up to a certain depth and then compared whether two or more of them are equal in their behavior. And that way we came up with 850,000 rewriting rules. So basically you could say we have a large lookup table with all identities. And the second thing, why is this the final expression? So why do we stop after expressing one part? Instead, we could run a recursive approach. We could treat this as our new expression. We could pick another sub-expression, replace that. They are still equal. It's still the same concept. And we could keep going like that. We could replace another and so on and so on. We could make this arbitrarily complex. However, for now, we just stop here and be done with that. So the second thing is we can use a recursive rewriting approach to make our expression as large as we want. Now there's an even more powerful categories of MBAs, and that's polynomial MBAs. The idea is the same. We want to pick our expression or a sub-expression and rewrite that. And in this case, we use a function h, and it's inverse function h minus 1. So we do need an invertible function. Unfortunately for us, we found one. The thing here is it's defined on 1 byte. We need to consider this. But then we can go ahead as before. We just replace our sub-expression with the more complex version. We apply the functions and we apply the inverse function. And that's how we arrive at a more complex representation that still does exactly the same. It still computes the same as the first one. So if you find that is a cool technique, I invite you to check out this paper or generally the work by the Quarks Lab folks over in Paris. They do a lot of work on this. Be not afraid of math when looking into that. All right. And with this technique, with using MBAs to generate syntactically complex operations, we conclude a number of techniques that together, when used, help us against all types of attacks. What's really the thing here is that there's not a single technique, not a single panacea, but we need the combination. All right, let's quickly see how we nail those two design principles. So we wanted to have a complex and target-specific thing where all the stuff is highly intertwined, and what we got were merged semantics. So you have to look at cross-handler level. We had the polynomial encodings to combine the instruction semantics of different handlers. We used point functions to stop the codebook checks, and we had like very complex data flow dependent expressions to stop synthesis-based attacks. And with our MBAs, we can prevent symbolic execution. Now, with this example of a next-gen VM, the question is really, what's the impact on deobfuscation? So obviously, obfuscation and deobfuscation is always an arms race, right? They shift around. But right now, with all these next generation obfuscation techniques coming into play, it feels a lot like obfuscation is significantly at an advantage, and deobfuscation is on the limits of what it can do. So what's the particular challenges we need to deal with? Well, due to the first design principle, our powerful synthesis attacks no longer work. And there's no longer meaningful mnemonics when we write our assembler. There's no longer an addition. There's something like neg, add, mul, x, or push, which is just weird. And due to the combination of VM components, our analysis is no longer like a single isolated handler. We need to look at the global picture. And this means we have to do a lot more work. We have to put in more effort, and also our tools reach the limits. So what needs to be done to overcome this situation, or what is currently being done to do so? That's the cliffhanger with which I hand over to Tim.
Yeah. Test. Thanks a lot, Moritz. So question rises now, given the strengths of obfuscation and the limits of current deobfuscation approaches, what are the next steps in deobfuscation research from academia, but also on the practical side? So what needs to be done? And the first thing is we do need better analysis tools. So right now, we have tools which work fine with showing us code, showing us decompiled code. Some work also quite well with obfuscated code. But everything that we have so far is mostly very limited and also mostly local. So we don't have really good tools which allow us to easily perform cross-function analysis or reason about multi-threaded applications. There are some tools in private, or some companies build them for very specific in-house purposes. But in general, there's no good tooling for this available for public. So we need some work there. And further, so we have limits in large instruction sequences. Let's take, we have a VM handler chain like that, where the one handler and the 100th handler work together in some form of encoding. And we have perhaps 1 million instructions or 10K instructions or 100K instructions in between. We would basically have a large number of things. And the analysis tools then start struggling because they have performance issues or go out of memory. So large-scale analysis tooling is not really available. And the other thing is, also, we do need advances for binary lifting. The future goes into using compiler-based approaches where we use binaries, lift them into an intermediate representation, and perform some large-scale analysis on the compiler level and spit out simplified binaries. Again, this is the future, or one part of the future, and therefore we do need better lifting from binary to intermediate representations. And yes, of course, everything of that is a really, really hard problem. Most of them, like interprocedural analysis or multi-threaded environments, are from a theoretic point of view undecidable. So yes, everything of that is fucking hard. But these are the things we have to work on to create better and usable tools that perform also in these directions. The other thing is the selection of analysis windows. Right now, we can't start with the first instruction, with the last until the last instruction and analyze anything in between, because the tools are out of memory, too slow and stuff like that, as discussed before. So therefore, we have to do some research about finding in some automated way sources and things or start and end points that allow us to simplify the analysis. So we need some strategies to isolate and simplify partial data flows. And we also want more research on the automated exploration of control flow and data flow structures in large code bases. So these are the things: better tools, more selection, some research on window identification boundaries. And then we also need some progress on MBA deobfuscation. Like, we can build really, really complex and hard until impossible to simplify MBAs, given that these formulas can be that long and can be distinguished between n different code locations. So, also from a mathematical point of view, they are hard to simplify. So, we do need some more research on polynomial MBAs and how to break them. We do need better strategies for synthesis-based approaches to reach higher depths. And we also need some ways to synthesize constants. Like, if we have expressions like that encoded in a very complex formula, we don't have easy ways to come up with these constants. However, in this area, some research has been done. This is quite active currently. So the research in the last year catches up on MBAs. For instance, there's this paper by De Novo, the guys who build game protections. They built something which is called efficient deobfuscation of linear MBAs. Linear MBAs are a certain specific subclass of MBAs which are really, really easy but widely used, especially in malware. And also some cheap obfuscators. And linear MBAs can be considered dead right now. There's also some research by the Hexrace guys who built and wrote a blog post about that. We basically, I think this went up in February this year, where they now have a decompiler plugin for Hexrace, where you basically have an MBA and can simplify or optimize it, and then you get simpler ones. But also this is really, really great tooling. But this only works with, or this mostly only works with linear MBAs, and also only on the function level. So no cross-function level. And for too large expressions, it also has some performance problems again. So there are also some novel methods, research-wise, how to apply and develop new techniques to basically trigger deobfuscation on polynomial MBAs. This is research from last year, which also works quite well. However, this is just blog post research. There's nothing around which is really efficient or which can be easily stacked to binary tooling or stuff like that. So there is some research code, but these are really early stages, and there has to happen more such that you can simplify your DRM systems in IDA with that. So, however, what we are saying is, in research, some things, especially on the MBA level, get better, but are far away from getting solved. And the other challenges remain. So most analysis tools are still they don't work in multi-threaded environments and stuff like that. The selection of where to start and where to end is not solved. And the actual deobfuscation, the actual research on deobfuscation has for practical binary deobfuscation a low impact. So, and therefore, its impact is there, but it is limited in practice. So, in other words, deobfuscation still is not feasible. And to conclude, there are three main takeaways today. Current VMs can be broken easily, more easily in terms of there is tooling, the approaches are known, it just takes time in a semi-automated fashion. So most of the VMs out there can be broken. The industry starts shifting towards novel VM designs, these high-class obfuscators, and the code deobfuscation research has to catch up, although there are some developments into the right direction. So, and therefore we conclude that next-gen VMs will shape the obfuscation landscape in the next years until deobfuscation might catch up. So this was from our side. There's a short summary. Otherwise, if you would like to contact us, feel free to reach out via Twitter or via our homepages, or we are also at the con the next days. So just we hang around, and now we are open for questions. Thanks a lot.
Well, thank you very much for the talk. Seeing the time, I think it's better that questions will be asked personally.
Okay.
So thank you very much, and a round of applause for our speakers.